Okay, so let's take a look at the last combination, which is a strong acid, weak base titration. And let's consider, for instance, the titration of HCl with which is a strong acid. Okay, so HCl is strong with ammonia, NH3, okay, which is a weak base. So here, what we're actually going to plot and we're going to see is we're going to start off with the weak base, and then we're going to be judging or measuring the pH as a function of the volume of the strong acid that's added. So because we're starting off with a base, we would expect the initial pH here to be high, right? More than 7. And this is a very important difference between this titration and the other ones, where the other ones that we saw previously, the pHs were starting off less than 7 because they were either strong acids or weak acids that we're starting off with. Okay, so here, the reaction generally between the HCl and the NH3, right? This will go to completion. We're going to have the H plus combining with the NH3 to form NH4 plus. We also get the Cl minus, so those actually combine to produce the ammonium chloride, or simply we can just look at the ions involved, the net ionic equation. We have our H plus plus the ammonia to produce NH4 plus, right? So we have our weak base, and we have the conjugate acid of that weak base. So what we will notice here is that the pH at the equivalence point, another big difference, is less than 7. Okay, and that's because the ammonium ion that is formed actually acts as a weak Bronsted acid. And because it does so, right, that NH4 plus in H2O will donate an H plus to the water to produce the H3O plus, the hydronium ion. We also get the NH3. And that's why that pH at the equivalence point is going to be less than 7. Now, you will notice, again, here we're starting off with, for example, the ammonia in our flask in this case, and we're titrating it with the HCl from the burette, right, as a function. So the volume of the HCl added in the burette is on the x-axis, and that's because the ammonia has a tendency to vaporize. It's very volatile, so it's best to use it in the flask rather than in the burette. So this is going to be very analogous to the titration of the weak acid with a strong base. Here, the initial pH of our system is going to be determined by the concentration of ammonia as well as the Kb of ammonia as well. Okay, whereas in the case of the weak acid strong base, we looked at the concentration of the weak acid and the Ka of the weak acid. So let's take a look at an example. So let's consider the titration of our ammonia. Let's say we had 25 mils of 0.1 molar NH3 with 0.10 molar HCl. Okay, so the initial pH, we're going to calculate using equilibrium table. Okay, so our ice table and the concentration of the NH3 and the Kb of NH3. So we have our NH. So all we have is our NH3 in aqueous solution. Right, that is going to form our NH4 plus, and then we're also going to get the hydroxide ion. NH3 initially here is 0.10 molar. So we have our 0.10 molar ammonia. Water we're not concerned with. None of the products to begin with. We're going to lose X along the way, add X on the products, and then we have our equilibrium concentrations. Okay, so we've done this millions of times already, not literally millions, but we've done it lots of times, and we can solve then for X in this case. Remember now, because this is NH3 acting as a base, this is going to be our Kb expression that we write. So that's NH4 plus times OH minus divided by our NH3. Okay, the Kb for ammonia, if we solve for it using the Ka for the ammonium ion, we end up with 1.8 times 10 to the minus 5. And then we're substituting our equilibrium expressions into our equation. Again, we're assuming here X is small. Okay, so when we solve for X, X here is equal to the concentration of the hydroxide. Okay, so that is going to be equal to 1.3 times 10 to the negative 3. So then I can determine the pOH from this, and then as a result, determine the pH, which is equal to 11.11. So the initial pH there is actually, like we said before, is greater than 7. Again, because we're using a weak base, we expect it to be more than 7. And initially, all we're using, before we add any acid to this, it's just an equilibrium problem using ice table, concentration, and the Kb value for that weak base. At the equivalence point, okay, so let's do a quick one here at the equivalence point. We can use the concentration of and the Ka of the conjugate acid of H3O. I'm sorry, the conjugate acid of NH3, which is the ammonium ion, NH4 plus, and also our ice table. Okay, so let's take a look at how we would do that. And that is, let's see, we got this example here. All right, so we have 25 mils of the 0.1 molar HCl, I'm sorry, 0.1 molar NH3 titrating against 0.1 molar of the HCl solution. All right, so once we start adding H plus to this thing, then the NH3 will react with any H plus from the HCl, and we end up making the ammonium ion NH4 plus. So at the equivalence point, all of the NH3 would be converted to NH4 plus. So what we need to do is we need to determine the concentration of the NH4 plus at the equivalence points using the Ka for NH4 plus to solve for the pH, right? So we need to determine concentration of NH4 plus, then use the Ka for that ammonium ion as well to solve for the pH. All right, so originally the solution would have contained right? So we have 0.1 0.100 millimolar or millimoles of the NH4 over 25 let's see, per mil, I'm sorry, per mil. Then we have 25 milliliters of it. Okay, so that's going to give us how much? 2.50 millimoles of the NH4 plus. I'm sorry, of the NH3. So in order to react with all of that, we would need 2.50 millimoles of the HCl to completely react with that. Okay, to react with the NH3. So what volume of the HCl would contain 2.50 millimolar? Well, we know what the concentration is, and we have how many moles we want. Right, so the volume there would simply be equal to the 2.50 millimoles of the HCl, and then the concentration of the HCl was what? 0.10 molar, right? So that's 0.10 millimole per liter or per mil. So we have per mil on top, and then 0.100 millimole, right? That's the concentration. We just flipped it as a conversion factor. So we end up then with 25 0.00 mils of the HCl that's needed. So it takes this much to react with that to get to the equivalence point. So the total volume then at the equivalence point would be equal to the 25 mils of the HCl plus the 25 mils originally of the NH3. So that gives 50.0 milliliters of solution at the equivalence point. So at the equivalence point, right, all of the NH3 originally present has been converted to the NH4 plus, and the concentration then of the NH4 plus would be however how much we generated of the NH4 plus divided by the total volume that we've had. Okay, so we have the NH3 amount, the 2.5 millimolar, and then 2.5 millimolar of the H plus from the HCl. These will react in a 1-to-1 ratio, so we're gonna have none of these left over, but we will produce the same stoichiometric amount of the NH4 plus, right? So we have 2.5 millimoles produced, divided by, so the concentration now of the NH4 plus would be the 2.5 millimoles divided by the 50 mils. So 2.5 divided by 50 would give us 0.0500 molar for the NH4 plus. So at the equivalence point then, right, we have our NH4 plus that is going to react in water as a acid. It will donate H plus to H2O to form H3O plus, and we also get the NH3. Now we can do our new ice table. So we have our 0.050. I'm not concerned about the water, none of this to begin with. We're going to lose X amount. We're going to gain X amount of these. We end up with 0.0500 minus X. We got X, we got X. And now we're going to solve for X, right? So we have this acting as an acid. So we have the Ka for that is equal to 5.6 times 10 to the minus 10 is equal to the H3O plus times the NH3 divided by the NH4 plus. Again, assume X is small to make the calculations easier. So we end up with this being X squared over 0.0500, and that's equal to 5.6 times 10 to the negative 10. So you solve for X, which is equal to the H3O plus concentration. X there is equal to 5.3 times 10 to the minus 6. So then the pH would be the negative log of that, which would give us, that would give us 5.28. Right, so at the equivalence point, the pH then ends up being less than 7, right? We rationalize why that was in the first place. Now we've gone through and done the calculation to determine why the equivalence point is acidic rather than neutral.